Hello, welcome to the introduction to linked data. Before we start talking about linked data itself, we need to think about what is wrong with regular, not linked data. For example, take a look at these two datasets. On the left, we have a typical tabular dataset. On the right, on the right, we have a typical JSON dataset. And here we already see the first problem. We have two different data formats, and for us to work with the data together, we first need to integrate the data into a single data format before we can actually do something with the data. But let's take a look at the other problems that are there with these data sets. The second problem is that the IDs, identifiers used in those data sets are actually not unique. Imagine that we will talk to our friend about the data here, and we'll say, hey, take a look at 1234, he's cool. And the friend says, which 1234? This one on the left or the one on the right? The one in the table or the one in the JSON file? Well, this is a problem thanks to the non-uniqueness of the identifiers used in the data. If they were unique, this wouldn't happen, right? Okay, so let's say that with a friend we talk about this and we decide that actually they meant the actor from the tabular dataset. Now there is another problem. The friend wants to access the data and get all the data records about that actor 1234, and they don't know where to get the data and how to get to the data. So again, we need to talk to the friend and explain where the data is, for instance, where on the web we can get the data, or on which CD or flash drive the table is saved. Then we need to explain to the friend that actually the data, when once opened, contains a set of rows, and in the column ID they will find the number 1234, and then they will have the data record. Well, this seems unnecessary, right? But that's how it is with CSV files or JSON files. Okay, we can continue with the next problem. Here, the tabular data set actually has a header, and as you can see, the header is in Czech. And the third column here, okay, let's say we know what it is in Czech. It says stars, but is it stars in or stars as? Because as we can see on the left, we have actors. On the right, we have movies. And now there is a connection because each actor stars in or stars as. And now here we get to the question, is it stars in and can we connect it to the other data set, or is it stars as and therefore we cannot use this value to connect to the other data set? Well, okay, so this means stars in, and really the third column is a link to the second data set, to the JSON one. So we can use it. However, because there are no unique identifiers, again, we don't know which movie it is that actor number 1235, for instance, links to. And there is a huge difference because one of the movies has a rating of 9.0 and one has 5.6. which is, of course, a huge difference. Imagine that you should go to see a movie with rating 5.6 at the cinema. You wouldn't be too happy about that, I guess. Okay, so these are all problems that are already there in the regular non-linked data, and all people working with data have to deal with those kinds of problems on a daily basis. Now, if we were to formalize the issues are ambiguous identification of entities in data, which means the identifiers of the data items are not unique. Then low findability and accessibility of the data, because even if I know the identifier and I know which entity it identifies, I don't know, based on the identifier, where to actually find the data. And finally, there is lack of contextual information, because when I finally get to the data and I see, for instance, 1, 2, 3, 4, Robert De Niro stars in Joker, well, I don't know which Joker movie this represents, and again, I don't know where to get the data about the movie. I don't have the context. So when we have issues, we need to have additional requirements which, when satisfied, will solve these issues, right? So what we would need is actually unique and global identification of entities in data. We need to increase findability and accessibility. Ideally, based on the identifier, we would want to be able to get the data and find the data. And finally, we would like to have some contextual information with the data. So once we get the data, we could also get some pointers to where to get additional data if we are interested. So now the question is there such a system that would actually fulfill these requirements? Well, there is one, and you all use it on a daily basis. The system is the World Wide Web. With one exception. The World Wide Web is based on documents, which means texts meant for people and meant to be read by people. So when we want to get some information from the web, it goes like this. We see a web page, we read the web page, I mean people, and we get some information from it, and that's it. But if we were to actually work with the data as machines, we would pretty soon run into problems. But we will get to those problems in a bit. Right now, let's take a look at the principles of the World Wide Web, because there are only 4. They are very basic, and implementing those 4 basic principles allowed the web to grow to the size we know today. So it is very successful and based only on 4 basic principles. So the first principle is there is one format for publishing documents, and that is HTML. The second principle is there are URLs as unique global identifiers of documents. And the third principle is there is HTTP protocol which can use the URLs to actually localize and access the documents. And once we get the documents, the fourth principle says that there are hyperlinks between documents. So there is a link from one document to another, and we can follow it if we want to get more information, and we don't have to follow it if we do not want to get more information. And in the space created by those 4 principles, there are 2 kinds of applications. Web browsers, which is what we use in our everyday life today. And then there are search engines, which index the texts which are encoded in the documents for people. Now, the web, as described now in this slide, is actually not exactly as we use it today, because today you don't actually type in the URL of a web page that you want to access. You use a search engine, you use the full text search capability of the search engine, and the search engine gives you actually the URL. So nowadays you don't even have to know the URL of the web page to get to it. And this is thanks to the search engines. So what we can do with the World Wide Web as we know it today, the web of documents? Well, we can publish human readable documents. We can see them in our browsers if we know the URL, or we can use a search engine if we do not know the URL, and we can follow the links which are present in the documents, and we can get more information like this. The important thing is that the person writing the document typically has more contextual information than the person reading the document. So it is nice of the person writing the document to include that contextual information in the form of links into the document so that the readers can decide whether they want more information or not, and they do not have to search for the information somewhere else. They have the links included in the page. In 2019, there was a 30th anniversary. In 2019, there was a 30th anniversary of the World Wide Web. And here in the picture, we see Sir Tim Berners-Lee, who is the inventor of the web. And Tim Berners-Lee actually coined the principles of linked data, which we will now talk about. So we will apply the principles that made the web of documents so successful, and we will apply them to data. So now let's go from the web of documents to linked data. But first, let me illustrate the problems that we have with the web of documents if we want to actually work with data. Imagine these websites. There are 5 websites in the slide, and they all have a lot of information about Prague. There is demography of Prague, public contracts of Prague, basic information, EU-funded projects, and Prague's budget. So very interesting information encoded in documents meant to be read by people and not by computers. Now imagine that you were to answer a query, one of these in the slide. For instance, money spent in Prague for new children playgrounds in the last 5 years per one child. Okay, so imagine that you as an IT specialist would have this task and these websites with all the information there. How would you proceed? Well, first, you would have to identify the websites actually containing information that you need to answer the query. So for this, we would have to see the list of public contracts and EU-funded projects. Then we would have to have the demography of Prague to see how many children are there. And when we had that, we would be able to actually answer the query if we had that in data. When this information is only in the websites, we can go into that manually, which would be very time-consuming, or we would have to follow some typical steps that every developer wanting to work with data nowadays typically goes through. So first, we would have to identify the website containing the relevant information. Then we would have to create a scraper, which is a script that goes through the website and picks the relevant information or downloads the whole web pages containing relevant information. Then we would, of course, have to parse those pages written in HTML to get the relevant info. Then we would have to pick a database and create a database schema for the integrated data from all those websites. And we would have to create transformation scripts, one per each data source. And then we would have to run them. And finally, when the integrated database would be filled, then we would be able to actually write a query answering this question. So this would be very expensive and really not ideal, right? Well, once we get to know linked data, you'll see how actually all those steps can be skipped and how data consumers can go straight to the last point, and that is just write the query and get the answers. That is what linked data is about. That is what linked data enables you to do. And that is what we will talk about in this lecture and the rest of the semester. But first, let's take a closer look on the state of the World Wide Web today. The situation actually is not that bad. It is a bit better than I described, because typically the websites contain information which is stored in an underlying database. However, the data from the database is still being encoded into HTML for human readability, and sometimes we do not have access to the underlying database, so we have to re-encode it from the web page to actual data. Nowadays, typically, when you have a website with useful data and the publisher of the website wants you to work with the data, they can actually publish an API. So this is the actual state of the web today, where when you have an underlying database, you also have an API which helps you to access the data without having to scrape HTML web pages and parse HTML. However, the rest of the steps still remains, because still each API is different. So you still need to identify the relevant APIs. You still need to learn the data format of that API. Some API provides XML files, some API provides JSON files, some API provides CSV files. So still we need to integrate the data into our database, create the schema for the database, and then we are able to query the data. So this access to data through APIs is a good step, but actually all it saves us is the hassle with parsing HTML files. The rest of the complexity is still there. And actually the complexity is illustrated by this nowadays famous illustration, the social network silos. Each of the silos here represents a social network with its API. And what it also represents is that each social network is a walled garden, a silo. This means that if you want to talk to your friends in another social network, you have only two choices. Either you join the other social network, or you persuade all your friends to join your social network. There is no interaction across borders of the silos. So imagine that you are a developer and or just a user of one of those social networks, and you want to send a message to all your friends. However, your friends have profiles on different social networks, and there is no way to send just one message to all of them. You either need to invite all of them to your web service, or you need to send the message many times, once per each social network used by your friends. So this is again not ideal. And why is that? Well, let's go back to the principles that made the web of documents successful, and let's compare them with the principles the current web is based on. So the first one says use URLs as unique global identifiers of documents on the web of documents. Each page has a URL. However, in the web or the data accessible on the web, there is no global identifier of things. There is global identifier of API endpoints, that is true, and within that endpoint you have some identifiers, but they are not unique and global. Now, in the web of documents, there was one format for publishing documents, HTML. In the data on the web, there is XML, JSON, CSV files, Excel files, etc. So many different formats, which makes working with data that much harder. Now, in the web of documents, there was HTTP used for localization and accessing documents by their URLs. In the current state of the web, you use HTTP to localize the API endpoint, and you can access it, but you actually do not localize data about the things. You only localize the APIs. Then you need to learn the specifics of each individual API. So again, this principle is not followed in the current state of the data on the web. And finally, the web of documents is successful because there are hyperlinks between documents. You can go from one document to another regardless of where the document is published and by whom. In the state of the data on the web, there are no links from one data silo to a data item in another silo. There are exceptions, but they are just that, exceptions. So this actually does not work also. So can we apply the principles of the web to data to make the situation better? Well, yes, we can. And that is what is linked data. It is a set of best practices based on the principles of the web applied to publishing data. And there are two main goals. One is machine-readable data on the web, semantically described. And the second goal is data which contains context, links to other data items, so that the data consumers can actually go through the links to get more data, or they can ignore them if they do not want more data, but they have the option, and the way of getting the data is standardized. I already mentioned Sir Tim Berners-Lee, and he defined 4 principles of linked data, which are deeply based on the 4 principles of the web of documents. And we'll go through them one by one, and we'll start with the first 2. The first 2 principles of linked data say use URIs as names for things and use HTTP URIs so that people can look up those names using the HTTP protocol or link to those names using bookmarks or whatever. To illustrate why it is important to follow these 2 principles, let us imagine a web of documents as we know it today, however, with the first principle broken, which means web pages as we know them today suddenly do not have URLs. What does this mean? Well, try to send a link to your friend saying, hey, take a look at this. Well, if web pages don't have URLs, you cannot do that. You need to explain to your friend where they can get the data, how to get the web page, how to get to it, where to find it. So that's almost unimaginable, right? But this is actually the state of data on the web. Well, remember the example from the beginning of the lecture. This is really the state of the data on the web today without linked data, because we have CSV file which clearly connects to something else. We had actors and movies, but but the individual actors, they don't have their own global unique identifier, so we cannot link to the individual actor we want to point to. That's crazy, right? Okay, so let's take a look at what it means to follow the first two principles of linked data. So here we have again data about Prague. And in the data about Prague, there are data entities like the Prague city, some EU-funded project, or the Prague Council. There is data about Prague demography, there is Prague public contracts, and so on. Each of those entities is a separate data entity. It's a first-class citizen in the web of data, which is a synonym to linked data. And when we follow the first two principles, we need to assign an HTTP URI to each of those entities. So we do just that. So for instance, for the green one, we assign HTTP praha.eu/city. For the Prague Council, we have praha.eu/council, and for public contract 7302, we have praha.eu/contract/7302. So we assigned a globally unique HTTP URI to each data entity we want to publish data about. Now, there are more publishers of data about Prague on the web, so they also follow the first two principles. So we'll have the Ministry of Finance publishing data about Prague's budget. So again, for each data entity, they assign an HTTP-based URI. And we have even more publishers, and each one follows the first two principles. So for each data entity, we assign a global unique URI. We can do that because we already have a domain registered because we publish our websites. So we can use that or create a subdomain for data. And within that subdomain or one of our domains, we can assign a globally unique URI. So that's fine. We can do that, and we did that. Now, maybe you already see a problem rising here, but we will get to that problem later. Now, the third principle of linked data is that when someone looks up a URI of one of your things, provide useful information using the standards. The standards mean RDF, which is the data model for the web of data, or Sparkle, which is a query language for the web of data. So again, to illustrate why it is important to have this principle in place, let us take a look at the web of documents, web pages. If the third principle was broken, what would it mean? Well, this would mean that actually we'll suddenly have web pages written in many different formats. So not only HTML, but there will be one page in HTML, one page in something else, and so on and so on. What it means is that you will need many different applications, or each of your applications would have to learn many different formats, and probably not all of them. So when you encounter a web page, you would first have to determine its format. You would have to first see if you have an application that is able to process that format, and then you would be able to actually see the web page. And not only that, each of those formats would probably have different capabilities. So maybe some of them would allow linking, some of them not, and so on. So it would be a mess, right? But actually, we know this situation because this principle is sometimes broken even nowadays. Remember, when was the last time you actually browsed the web on, for instance, your phone, and suddenly you found a link which downloaded a PDF file or a Microsoft Word file, and you had to install a PDF viewer or Microsoft Word viewer to be able to actually open that file. And what was inside? Well, there was text, which could as well be published as HTML, saving you the trouble with finding the right application, installing it, and having many applications installed on your phone just to be able to read texts, right? So this is again a problem. And in the web of data, in linked data, the third principle says that data on the web is published in RDF. RDF is Resource Description Framework. We will have a lecture on RDF later, so this is just a brief introduction to RDF. Now, RDF, the idea behind it is that we will break down all data into simple statements, like the one we see in the slide. Jakub Klimek studied at Charles University. This is a very simple RDF statement, or just a statement. And in RDF, actually, we can view this statement as an RDF triple, where the first part of the triple we call a subject, the second part of the triple we call a predicate, and the third part of the triple we call an object. And the subject is the entity we say something about. The predicate says what we say about that entity, and the object gives us the value of that predicate. So here we have a subject, Jakub Klimek. We say that Jakub Klimek studied at, and Charles University is the value of the studied at predicate. So we have a subject, Jakub Klimek, studied at, predicate, Charles University, object. Subject, predicate, object, and RDF triple, a simple statement. And we can also view this simple statement graphically. So we can have a node in a graph. One thing I forgot to mention is that these statements, when we have multiple statements, they form a graph data model. So we have nodes represented by subjects and objects, and edges represented by predicates. And there is the graph is orientated, so the edge, the predicate, goes always from the subject to the object. So graphically, we can view it as a graph. We have nodes in the circles, and we have edges which are labeled. So we know that this edge between Jakub Klimek and Charles University is labeled by studied at. Now, RDF is a data model. So it says that all data form a graph, and the data is represented by RDF triples. But this doesn't say how the data should be represented, for instance, in a text file, or how they should be transmitted over the internet. That is why there are syntaxes or serializations of the RDF data model, and actually there are 7 standard serializations of the RDF data model. Some of them are native to RDF, and some of them serialize the RDF data model into other data formats like XML or JSON. We will get to those standard serializations in the RDF focused lecture, but right now we'll stick to just one of those notations, turtle, and I'll explain it right away. Now, if we only had one triple or one statement, that wouldn't be too useful. So we'll add 2 more statements here, and we have a small graph about a public contract published by the city of Prague. And we can see the subject in the blue oval is the public contract 7302. And we say that this contract has a contracting authority, which is the Prague Council. The public contract has a name, which is Playground Revitalization. And the public contract has an estimated end date, which is August 31st, 2011. So 3 simple statements. But already we can see that there is another type of a triple, another type of statement. because before we had a statement connecting two resources, two things in the RDF graph. But now we have the second and the third triple actually connecting a resource, the public contract, to a trivial simple value, like the playground revitalization, which is a string value, or the estimated end date, which is a date value. These data values are called literals. So we have two types of triples. One connecting two nodes of the graph, two resources identified by IRIs, two things. And the second type connects a thing to a data value called a literal. Now, the edges in this picture are named using plain English. So we can see that the edge on the left says contracting authority. But if the edges were actually named like this by a text in English, there will again be, or there would be a mess in the data, because someone else would call it something a little bit different. So actually what happens is that even the predicates are things identified by IRIs uniquely, globally. And when we want to know what the predicate actually means, we can always go to that IRI and find out. So here the data is the same. However, the predicates are now represented by IRIs. And this is actually how it looks like in the RDF data model. So an RDF triple, or the simple statement, consists either of 3 IRIs or of 2 IRIs and a data value. Now, for practical reasons, because the IRIs are rather long and they wouldn't fit nicely onto a slide or read nicely, I will introduce a technique called prefixing, and I will contract, or I will shorten the IRI like this. There is a string, then a colon, and then another string. And the string before the colon actually represents a part of the URI called a prefix. So this and this is the same, and we can still read them as full URIs. They are just shorter and nicer to read. Now we'll add more data. So now we'll have the 3 RDF statements we had about the public contract, and we add another node to the graph, another thing, and the other thing will be the price of that, the agreed price of that public contract. And that price is actually a structured value which has the value itself, and then it has currency. So 2 more statements, and one connecting the contract via the agreed price predicate to the price entity or node or resource. Now, this graphical representation still is not how it looks like actually on the internet when we want to send this data from a server to a client, let's say. How it looks like actually is this, and this is the turtle notation, turtle syntax. It is a compromise between machine and human readability of the data. And we can see that we still have the subject, which is the public contract 7302, and then we have all the statements about this public contract. And the last, actually the next to last one, the agreed price, connects to the URI of the price specification, which then continues in the bottom part of the data. So again, then it plays the role of a subject, and we have 2 more statements about the price. So we can see that one node in the RDF graph can pose as a subject and an object in one piece of data. It also shows good structuring of the data, because in CSV files you often find price as one column which contains both the value and the currency, which is not good practice because those are two things. And in RDF, this is actually a rule that you should structure all values straight down to atomic values. Now, before we finish talking about the third linked data principle, which says when someone looks up a URI, provide useful information using the standards, and now we know what the standard is, that it is actually RDF. There is one more thing we need to talk about, and that is, what do you do when you see a URI as a user? Well, typically you take that URI and you place it in your web browser and you see what's there, right? But when we start using the URIs for data in RDF, that is typically not what you want to see when you access your URI. Well, there is a neat solution baked into HTTP itself, and that is the accept header. Each HTTP client, when they do an HTTP request, they specify in the accept header in which format they would like to see the representation of the resource identified by the HTTP URI, by the URI. When you are using your web browser, they ask for HTML. When you use your application, which wants to see data, they can ask for RDF. So a single URI actually represents the resource, and you can specify in which format you want to see the representation of that resource. So with one URI, applications can get RDF and your web browser can get HTML, and it works together. Now, the fourth principle of linked data says include links to other URIs so that they, meaning users, can discover more things. So this is similar to links in the web of documents, so something like this. And again, let's have a look at what happens when this fourth principle is broken for the web of documents. Well, you all use Wikipedia, right? So there is a Wikipedia page about Prague. Now imagine that all those links that you can see there just disappear and there is pure text. Well, you read about Prague, you discover something nice, and then you can see that it is the capital of the Czech Republic and you want to see something about the Czech Republic. But you do not have the link in there, so you cannot just click through and see the page about the Czech Republic. You need to go to your search engine and you need to search for information about the Czech Republic, and then you need to pick a page and then you need to read, and you'll see that the Czech Republic is in Europe. So again, there will be no link, so you will again have to search for pages talking about Europe and so on. So very inconvenient, right? Without the links. But that is the state of data today without linked data. There are no links to other relevant data. There is no context. So what does it mean actually for our publishers to follow the fourth principle? Now, the publishers already followed the first two. They assigned HTTP URIs to all the data entities, and when you access the HTTP URI, you get data in RDF. So the third principle is also implemented. Let's have a look at the fourth principle. So the fourth principle says include links to other URIs. So it can look like this. For instance, the green one on the upper left talks about Prague, and the link there says Prague has demography, and it links to the Czech Statistical Office, to the purple one, to the demography of Prague. Now, these are RDF triples the same as the other ones. So there is no difference other than that the object is from another domain, another publisher. But from the point of view of RDF, this really doesn't matter. it is represented, the link to the demography, it is represented by a triple which is the same as any other. The same goes for the council and the budget connection there, and so on. So using RDF, you can easily include links to other relevant data entities. And there is one problem that I already indicated was there, and that is that, as you can see, 3 of the 4 publishers assigned their own URI to the red entity, which actually is one real-world entity, and that's the Prague Council, for instance. And the same goes for the green entity. Again, for the green entity, we have 3 different URIs by 3 different publishers. Now, if we want to connect the data, or if we want to work with the data as with a whole data set, we'll have data about 3 different subjects in the RDF graph, all representing the same real-world entity, but we as application developers will not know that these 3 different URIs actually represent the same real-world entity, the city of Prague or Prague Council. Well, of course, this happens naturally when you follow the first 3 linked data principles. And that is why there is a special predicate, our same as, that all linked data practitioners know about. And this predicate says that the IRI in the subject and the IRI in the object of this triple represent the same real-world entity. So actually the data can be integrated when those are linked, and it is quite standard that one real-world entity actually has many IRI identifiers. Well, and still we have some artificial borders here, because we still have the borders representing the individual publishers. The web of data actually looks like this. So you can just follow the data, you can just follow the links, and you don't have to think about who actually publishes this piece of data and that piece of data. It's the same principle as you browse through web pages today. So this is how the web of data looks like. And if we go back to the principles that made the web of documents work, and we compare them with the linked data principles, we can see that they are almost the same. For the web of documents, we had HTML as a single format to be used. In linked data, we have RDF as a single format to be used. We had URLs as global unique identifiers of web pages, and now we have URLs as global unique identifiers of entities. We had the HTTP protocol as the universal protocol for locating and accessing documents, and we have the same one for accessing and locating data about entities. So again, the infrastructure is already there from the web of documents. We can just use it and have a web of data. Now, documents included links to other documents, and with linked data, data can contain links to other data. And then there is something which was not there before in the web of documents, and that is vocabularies, which are standards for common data representation, and we will talk about vocabularies later. Now, linked data is a technical interoperability solution. It addresses some data interoperability problems, not all. This is how the web looked like before linked data. So we had data in different various formats, accessible using various protocols and various rules. And by applying the linked data principles, we end up with something like this. So the data starts to look more the same. The access methods are a bit different, but they follow the same principles. There are the different vocabularies, so they are represented by different colors of the circles. But as you can clearly see, we are closer to making the data look more the same, more uniform, and more easy to work with. Now, coming back to the original example, if the data from those websites were actually published as linked data properly, the data user could just translate the query given in plain English into a query in Sparkle, for instance, which is the query language for the web of data, which is similar to SQL for relational databases, and just write the query and get the answer. So they would skip all the data integration and parsing steps. So that is what we want to achieve. What is the ultimate goal in the web of data? Well, the question is, will it be successful? Well, the web of documents is successful, and it is based on just the 4 basic principles. And we applied those principles to data, so we can assume that the web of data will be as successful, right? Well, let's have a look. In 2007, this diagram representing the map of the web of data was first created. It consisted of 12 datasets. The circles in this image represent the individual datasets, which each consists of a set of triples. And the bigger the circle, the more triples in the dataset. Now the edges between 2 datasets mean that there are RDF triples in the first dataset which have subject from the first dataset and object from the second dataset. And the width of the edge means or represents the amount of those linking triples or links. Those triples which have subjects in one dataset and objects in another dataset are called links. And the sets of those links are called link sets. So this is what the diagram represents. Well, in 2008, there were already 32 datasets, and we can see that there is one dataset kind of central, and that is DBpedia. And DBpedia has definitely something to do with Wikipedia, right? Well, imagine you are writing a thesis and you want to reference some term, for instance. Where do you turn to? You turn to Wikipedia, because Wikipedia has a record for virtually anything, right? So you can always find something in Wikipedia that you can reference. Well, DBpedia took what is called a Wikipedia info box. If you take a look at a typical Wikipedia page about, for instance, a country like the Czech Republic, on the right side there is a so-called data box with some structured data. The DBpedia project took those data boxes from all Wikipedia pages and they created RDF data out of them. And that became the DBpedia dataset. Now, the DBpedia dataset also contains data about almost anything. So if you want to apply the 4th principle, add context, add links to other datasets, one way you can achieve that is by actually linking to DBpedia, because you can always find something in DBpedia to link to. So that's why DBpedia became so central in 2008. This is 2009. The colors represent data domains. So the pink color on the bottom is the medical domain. The green ones are literature. The purple ones are media. The orange ones are user profiles, and the yellow ones are governmental data. Well, this is 2010, this is 2011, 2014, 2017, here they changed the algorithm, and 2018, 2019, and it still grows. So one could say that it seems that the linked data will be successful. However, there are of course new issues that came up when people actually started applying the linked data principles to their data. And those issues included data suddenly coming offline, or data which is no longer maintained, versioning issues, and so on. But we won't get into that right now. We will, however, get back to the fifth principle or fifth point in the principles comparing the web of documents and linked data. For linked data, we had, in addition, vocabularies. Now, coming back to the original example with the playground public contract, we had IRIs of predicates. So, and I mentioned that you can access that IRI to see the definition of what that predicate actually means. Well, these definitions of predicate meanings and their URIs, those definitions form vocabularies. So a vocabulary is a set of definitions of predicates, their meaning, and their identifiers in forms of URIs. So for instance, we have an IRI for a name of a document, an IRI for the predicate representing the contracting authority, and the predicate representing the estimated end date of a certain public contract. Well, predicates are one half of what you can find in vocabularies. The other half is classes. Classes are or represent types of things. So you want to say that the entity represented by the URI praha.eu/contract/7302, that this entity is a public contract, we do it by this special predicate RDF type. So we have the subject, the IRI of the public contract, the predicate is RDF type, and the object is again a resource. In this time, the resource represents a class, and we can say it's a type of a thing. So here, the predicate says the entity is of a type public contract, where the public contract is a class which can be assigned with the RDF type predicate to every instance of a public contract. And the classes, the identifiers in the form of URIs and the definitions, the meanings of those classes are the other half of what comprises a vocabulary. So vocabularies are definitions of classes and predicates in some domain, and they define also their unique identifiers, IRIs. Now, you may have a question, where do I find the right vocabulary for my data? And the answer is there is a registry of vocabularies called Linked Open Vocabularies. And in this registry, all vocabularies used on the web of data are registered. So this is where you come when you search for a vocabulary to be used in data. Now, the diagram you see in the slide represents represents the individual vocabularies, and the bigger the circle of the vocabulary is, the more reused by other vocabularies this one is. There is one principle when creating a vocabulary, and that is that we do not create a new term, a new predicate or class definition for something that is already defined in another vocabulary. So for instance, here we see DC terms and DCE. Those are prefixes of Dublin core vocabularies, and Dublin core vocabularies contain predicates and classes for documents. So if you want to say that something has a title or something has a creator, we go to Dublin core for that, and we do not have to redefine this predicate when we create a new vocabulary. So the biggest vocabularies in the diagram are the most used ones in the web of data. Now, it could seem that linked data is the ultimate goal, but it is not. It is, as I already mentioned, a technical interoperability solution but it only gets us so far in the middle of the slide. If we want to continue and really publish data in a way which enables the users to treat all the data as one big distributed data source, we have to focus on data quality further beyond linked data. So linked data is a prerequisite for the true web of data, but it is not enough. We need to think about data quality, which has many dimensions, and we don't have to go into that right now. This is just to illustrate that linked data is not the ultimate goal. It is just a prerequisite for a true web of data. Okay, so now we have went through the introduction to linked data. We briefly described what it is and what are the principles. And now we will briefly describe how you can actually publish your own linked data. So first of all, if you want to publish your data as linked data, you need to know what is actually your data. So you need to analyze your data and create a data model or a structured domain description of your data. In this image, we can see a description of a data set containing public contracts. So we can see that there is the main entity, the public contract, but then there are other entities, organization or price specification, and there are many links between those entities. And this is a map of the data that we want to work with. And this is also something I will want from you in your semestral project. And this is the first step, to know what we are actually working with. This is also a UML class diagram, by the way, but you can choose another formalism for this, but UML class diagrams are the most commonly used ones. Once we know what we are dealing with, we need to do two things before we actually transform the data. First, we need to know which vocabularies we will use, which means which predicates and which classes we will use to represent the data we have in the web of data. This includes going to the linked open vocabularies and covering our data with existing vocabularies and defining our own where there is no suitable vocabulary to be used. So that's one thing. The other thing is we need to create IRI patterns, which means some rules according to which we will assign unique identifiers to the data entities we will produce. So we need to decide which domain we will use. We need to decide on the path of the URI. We need to know where we get an ID for each individual data item of each type we want to publish data about. So these are two things we need to think about before we actually get to the transformation. When we have those two things thought through, we can adjust the UML class diagram like you can see now, where we actually, instead of the entities, we have classes with the URIs, and instead of properties or attributes, we have predicates we will use for those properties and also the links between the entities. So when we have all this and we know how the IRIs will look like, we can actually export the data as linked data. This will result in a data dump, for instance. So a huge file containing the triples created from our data. The next step is data publishing. So once we have the data in the correct shape and form, there are many different ways of actually publishing the data. One of the techniques we already went through. That's the third principle of linked data. When someone looks up the URI, give them data in RDF, basically. So that's called IRI dereference. IRI is a reference, so when we use it, we dereference it and we get the data. This way, we can always get data about one entity, right? But if we want to, for instance, get data about all the entities in some data set, for instance, all the public contracts, we will probably need something called a data dump, which is one huge file containing all the data that we can download. On the other end of the spectrum is a Sparkle endpoint, which is a web service which is an endpoint to a database. So a database which works on top of RDF data loaded with the data that we just created and exposing a Sparkle endpoint, a web service to which we can send a query in the Sparkle query language, and we can get the results according to the query. So this can be computationally expensive for the publisher, but it is extremely comfortable for the consumer. On the other hand, publishing a data dump is very cheap for the publisher, but working with the data dump is quite expensive for the consumer. And somewhere in between, there are some other techniques which we will not go into. One of them is linked data fragments. Now, I was talking about Sparkle endpoints and RDF databases. The RDF databases are called triple stores because they store RDF triples. Nowadays, there is a great selection of triple stores you can choose for your use case. There are open source triple stores like OpenLink Virtuoso, Eclipse RDF4J, Apache Jena Fuseki, but there are also enterprise grade triple stores, which are of course paid, but they give you some nice properties, like they can be deployed in the cloud, like Amazon Neptune. They can be backed by a powerful relational database like Oracle Spatial and Graph. Then there is Stardog and others. The important information here is that you can choose. You can play with the data in open source software. It can even be enough for production, or you can implement linked data in an enterprise grade triple store, which you pay for. It's up to you. You have a choice. Now, there are also tools which support you in transforming your original data to the linked data representation. One of those tools is LinkPipes ETL. This tool is developed at Czech universities, and it is used worldwide for creating data transformation processes in a graphical way, like you can see in the picture. They support you in debugging the transformations and moving the data from the source to the target, for instance, a triple store or a file system. Now, you may have already seen a term linked enterprise data or a term knowledge graph. Both of those terms relate to linked data principles being applied to private data of companies. You may recall, or you may be familiar with the term intranet, which is the principles of the web of documents applied to documents inside an enterprise, a company. So it is a part of the web which is not accessible from the internet. It is accessible only from the inside of a company. But all the principles are the same. The web pages have URLs. They are written in HTML. They are accessed using HTTP, and they contain links to other documents. Well, similarly, knowledge graphs are centralized data stores inside companies which apply linked data principles. So data entities are identified by IRIs. They are accessed using HTTP. They are represented in RDF. So they may not be accessible from the internet, but they can link to entities which are published on the web. So knowledge graphs or linked enterprise data are the intranet of data. The same principles applied within corporations, enterprises, companies. Now, an illustration of how that can work within a company, this is actually how a movie gets produced. And this is a result of a project that ran in one of movie studios. And each step of the movie production process was represented by a system which was implemented to support that individual step. However, those individual information systems were, of course, represented or implemented in different times, and each of those systems had an input format and an output format. And if it happened that one system wanted to consume data coming from another system, a special transformer had to be created for this exchange of data. Which led to a huge amount of transformers. And if a new system came, it had to implement transformers to and from all the other systems it wanted to interact with. A solution to this problem was creating a knowledge graph, a intranet of data, an RDF store, to which all the data coming out of those systems were transformed, and therefore all the systems could also take data only from the RDF representation, from the linked data representation. And therefore, when an additional system came, they only had to implement one transformer for data from the linked data store, and one transformer to store the data back in the linked data representation, which greatly reduced the number of different transformers, and it lowered the complexity of the whole system. Well, so those were linked data applied either on the web or within an enterprise. And what's next? Well, these principles were formulated, well, now it's almost 15 years, right, ago. So it's not new. It's just starting to gain traction right now. However, Tim Berners-Lee is already thinking about the next thing, and that is the re-decentralization of the web. You see, the problem is that majority of interactions with the web are with a few giant companies like Facebook or Twitter or Instagram and so on. And the problem is that if you want to use the service, you need to have all your data with that service. You cannot say, I want to use Google Drive, but I want to access it from another application. And you also cannot say that I want to use the Google Drive interface, but I want all my data stored somewhere else. If you want to use Google Drive, you need all your data to be stored with Google. If you want to use Facebook, you need all your data to be stored with Facebook, and so on. So the applications are tied to the data. And this is a problem because you are not in charge of your own data. And there are already some scandals connected to this, like the data from Facebook being misused for election campaigns and so on. And this is what is wrong with the web today, according to Tim. And re-decentralization of the web is what can be done with that. And it is represented by decoupling of data from the applications. So the idea is that you can have your own data, and you can give access to different access to the data to different applications throughout the web. And if you are not satisfied with that application, you can just choose another application and use that other application to work with your data, which is something that is not possible with services like Facebook or Google. And this idea is represented by SOLID, social linked data. it is a set of conventions and tools for building decentralized applications and decentralized data storages. So with Solid, you can have your own data pod, personal online data storage, and you can store all your data in there. And then you have applications which can work with those data in your data pods, and the applications really work with the data in your pod. And if you want to use another application with the same data, you can. So you do not have to copy all your data to the individual applications. The applications go to the data you have stored in your pod, and you have control over your data. You can say which application has access to the data and which application does not have access to the data. If you are not satisfied with the service you get from one application, you can go to another, and you don't have to move the data. You just rearrange who has access to data and who does not. So this is briefly Solid, and we will get back to that and the technologies that enable Solid later in this course. Just to mention, Inrupt is a company which received a grant, some money, to make Solid viable also for companies. So they actually create commercial products on top of Solid. There are also community-based products for Solid. So the whole ecosystem actually is what is happening right now at this moment in the web. One more mention I will make is about open data. Open data and linked data. How does this work together? Well, open data is a way of publishing data so that everyone can work with it, both technically and legally. And there is this 5-star ranking scheme of maturity of open data. And now I will talk a little bit about what the scheme represents. So the first star of open data is when you publish your data technically in any format you want. It can be a PDF containing a scan of a table, for instance, so a nasty thing to work with. However, if you attach an open license to it, saying that everyone can do with the data whatever they want, you have 1-star open data. Then, if you want to make the data technically better, you publish the data in the format you actually work with the data. So if you work with the data in Excel, you publish the data as an Excel file. If you do this, so structured data remains structured, you have 2-star open data. 3-star open data is when you use open formats. You see, Excel is not exactly an open format because the specification is not freely accessible on the web, or actually was not in the past. It is a little bit better now, but still it is way too complex. So there is a better format for tabular data, and that is CSV, or there is another for hierarchical formats. There is XML and JSON, or RDF for graph-shaped data. So those are open formats that you can use. An open format is a format which has a specification freely accessible on the web, and everyone is able to freely create an application that is able to work with data in that format. So that is 3-star open data. An interesting fact, in the Czech Republic, there is a legislation saying that if you want to publish open data, it has to be at least 3-star open data. So 2 and 1 star is not called open data in the Czech Republic. Then the 4th star is when you start identifying your data entities using URIs. This basically means that you also use RDF as the data representation model, because there is currently no other model that allows you to use URIs natively. So that is the reason why 4-star open data typically is represented in RDF with entities identified by URIs. And the 5th star is when you include links to other datasets and you create linked data out of your data. So if you have linked data and you attach an open license, you have linked open data, LOD, and this is the 5th star of open data, the highest openness you can achieve. So this is where linked data and open data actually meet. And this is also the end of this first introductory lecture.